It feels like an eternity, but it's really great to be back. Back then I had another perf talk. Did anyone attend that? One person? Thank you so much for coming back. I hope you will enjoy this talk too. And to the rest of you, thank you for caring about performance, and thank you for spending your afternoon here with me today. So I don't know about you, but I often get the feeling that software might not be as fast as it possibly should be. But how fast should software really be? It's not an easy question to answer. And obviously, it depends on the code we write, but it also depends on the hardware. Today, we will look at how different ways of writing code has an impact on their performance. But to give us an idea of just how far we can go, let's start by looking at the hardware. This is my first computer. It's a Sword M5. It's a great little machine with a very weird quirk that my friend Mads Torgersen reminded me of. Take a look and see if you can find the space key on the keyboard. It's a very weird keyboard, but I wrote a lot of code on this. I wrote a lot of games. I wrote sprite editors and font editors, and I even did well, I guess it was an assembler, but it wasn't too advanced. By today's standard, this was not a fast machine, but it never felt slow at the time. It had a Z80 processor running at 3.58 megahertz. It had no multi-level caches. It had no pipelining, no fancy instruction reordering. The idea of multiple cores was science fiction at the time. This laptop, which isn't a especially fancy laptop, has an Intel i7, and these days, even clock speed is something that's advanced. So it doesn't just have a clock speed, it has a range, and this one will go from 2.3 gigahertz to 4.7 gigahertz. At home, I have a desktop machine with an AMD Ryzen. It has a speed of somewhere between 4.5 gigahertz and up to 5.7 gigahertz. So in terms of raw clock speed, we're at least 1,000 times faster. The laptop here has multiple cores. It has actually 20 logical cores. My machine at home has 32 logical cores. So we're not only 1,000 times faster, we are more like 32,000 times faster than my first computer. This is the car my dad owned when I was a kid. If we're being generous, it had a top speed of 150 kilometers an hour. My wife and I have a Kia Optima, so I guess I take after my dad when it comes to not buying fancy cars. But I do think it, by all accounts, it is a better car, and it's faster too, but not by a whole lot. What would it look like if my car had seen the same speed improvements as my computers? How fast would that be? This is the North American X15. It has a top speed of just shy of 7,300 kilometers an hour. It's the fastest manned plane there is, but it has nothing on my imaginary car. My imaginary car would still be 600 times faster than this. It would be so fast that I could go from Malmö to Seattle, where Mads lives, and back again about 300 times in an hour. That's how much hardware speed has increased in just a few decades. We have an insane amount of computing power at our fingertips. Software should be blazingly fast, but it isn't. I think Petrovsky hits the nail on the head here. Somehow, we continually make our software more complex, which makes it slower and offsets the massive speed improvements that the hardware that we have seen for the hardware. Sure, my new computer is a lot faster than my Sword M5, but I never really get the feeling that we're zooming back and forth from Seattle to Malmö when I run any software on it, right? It's faster, but it doesn't feel like it's 30,000 times faster. Instead, we have progress bars and UI hangs. So why is software slow? Well, because it isn't optimized, you can say. And that's probably part of it. But so let's look at that. Here are two very simple methods, or declarations for adding, methods for adding numbers. Assume that they do, exactly what it says on the tin, and that they're implemented in the most obvious way. If you had to pick the fastest, my guess would be that you would pick number 1. But number 2 has its merit too. For one, it doesn't have the same restrictions as number 1. Like number 1 can only handle integers, right? 2 is more versatile in that way. It can handle integers and floating points. It might even be able to handle complex numbers, Roman numerals, whatever. By all accounts, it's a better choice in terms of being versatile, but it's going to be significantly slower than number 1. So let's optimize it. Now, 2 is optimized. We're using the fastest text parser there is. It doesn't get any better than this. Like, this is as good as it gets. Does anyone believe that 2 will be faster? Probably not. My bet is that number 1 is still going to be orders of magnitude faster. In the very best case, number 2 might be on par with number 1, but most likely it will be slower in all cases. We can't solve every problem by optimizing. If we only need to add integers, then number 1 is clearly a better abstraction than number 2. But why would you even write a function like this? This is just plain stupid, isn't it? It takes strings. Well, if you're doing web development, you might have something that looks like this. But you might be, but Brian, this takes integers and returns an integer. Well, it does. So in that sense, it looks like number 1. But if you've done any web development, you know that's not how it works. ASP handles all the weird, figuring out if these texts are actually numbers and translate them into numbers for you, and then they call your method. And when you return your result, it'll do the whole thing again and send it over the wire. So just because there's code that we don't see doesn't mean that we don't pay the cost of that. So when we write code like this, it's going to be much, much slower than if we call a local method. For web services, we can't really get around this, but the lesson here is all this additional work takes additional time, and this makes your software run much slower. Herb Sutter calls this pessimization. And premature pessimization is when we accidentally or intentionally write code that does extra unnecessary work that slows the software down. And I think that's a real complex in most cases. And we'll see how we can speed up the code simply by not doing extra work, simply by avoiding pessimization. Writing the simplest code that we can think of goes a very long way for better performance. Obviously, if we need to, we can take a step further and actually optimize the code, and then we can make it even faster. But I think you'll be surprised to see just how much faster the code gets if we just avoid the silly stuff. So the time to complete some task depends on what we do and how we do it. If I'm making pizza, then the time it takes to make the dough, the time it takes to make the sauce, the time it takes for me to cut all the toppings all contribute to the total time. The faster I can do each of these tasks, the faster I can get the pizza ready for the oven. However, if I'm cleaning the kitchen, answering emails, practicing my guitar skills while I make the pizza, then I'm doing a lot of stuff that doesn't contribute to the task at hand, and it ends up taking longer, and it's less relevant how fast I can cut the toppings. Before we optimize, we really should make sure that we're only doing the work necessary for the task at hand. That's not optimization, it's just plain old engineering. So what we do is often more important than how we do it. It doesn't matter how fast we can do something if we don't need it. Like, doing nothing is always going to be faster than doing something fast. And we should start by making sure that we only do what we need to do. Once we have that, once we have an implementation that solves a problem, we can optimize the code if really needed. So here's a more specific example. This is from when I worked in the Windows division. My job was to look at partner apps and provide feedback on how developers could improve the performance of their apps. And we had this one sports app that, upon startup, would show you results for the current games. Unfortunately, the startup was a bit sluggish, so I took a look at their app. When the app started, they would make an HTTP call to retrieve an XML file with the results of today's game. Then they would get all of yesterday's results, and the day before yesterday, and finally they would load all of tomorrow's results. This approach might be simple from a coding point of view, but it's obviously not the simplest thing we can do. So how can we improve this? Well, obviously, all of the gray files, we don't really need to load them at startup because they don't change. Right? Tomorrow's games have not even been played yet. It doesn't make sense to get that file. And in fact, we don't even need to load them at all as part of startup because we are only interested in showing you today's results. So all of this is redundant work. What about today's results? We need to load something. We want to display results, so we need to load something. But how can we make this more efficient? Well, very simple, right? We don't need to get all the results every single time. We can just have a bookmark or whatever you want to call it and keep track of what the results we have received and then only ask for the results that have come in since that. If we do that, we reduce the amount of data we need to retrieve and process. And I think XML is a poor abstraction in this case. XML offers both structure and data, which is great for something like HTML, where the structure itself is important for rendering a page. For transporting data, XML is rarely a good choice. It has a really poor signal-to-noise ratio, and we've all seen XML files that are just, a bunch of tags, and then somewhere in there, there's a number 42 that we really need. Handling XML requires a lot of memory, a lot of processing, and it just leads to a lot of redundant work. If we just need the data, there are better options. So if we made the changes we just talked about, I think the app would improve. But the only way that we would know is to measure the performance. Measuring performance can be complicated. There are lots of pitfalls that we should avoid. I've seen many mistakes when people try to measure the performance of their code. But fortunately, the good folks behind benchmark.net has made it a lot easier. So measuring performance these days is very accessible. I'll use benchmark.net for the rest of the examples in this talk, but just in case you're not familiar with it, let me give you a brief introduction. So to run benchmark, we create a class that has a couple of methods that represents the benchmark we want to run. In this case, we are comparing MD5 with SHA-256. So we decorate methods with the benchmark attribute. And you'll notice that I set the MD5 method as the baseline, and I'll get back to what that means in a second. In our main method, we simply tell benchmark.net to run our benchmarks, and then it does all the hard work. It makes sure that we're running on a release build because we don't want to measure performance for a debug build. It makes sure that JIT compilation is not factored into the timing. It makes sure that it runs multiple runs so we can get a stable set of results that we can compare. And it does all the necessary work. And really, if you're doing benchmarks, you should be using this. Now, the downside of using benchmark.net, because it's thorough, it takes a little while to run the performance test. So I won't be running any live tests today, but all the code is on GitHub. So if you want to play around with it and see if you get the same results, you can. Once the test is done, we get a report like this, and you'll see that we have the operating system, we have the .NET runtime, we have all those sort of metadata details listed, and we have the results for each of the benchmarks. You see that MD5 has a ratio of 1 because we marked it as our baseline, so all other measurements will be in relation to that. The SHA-256 in this case has a ratio of 0.31, which means that it took about 30% of the time to run, which is about 3 times faster. If we get a ratio above 1, it means that it ran slower than our baseline. So a ratio of 2 would mean it took twice the amount of time to run. So hopefully you are now well versed in understanding these results, because I'll be showing you a lot of them. As we saw, the way we write code can be the source of pessimization if we pick the wrong abstractions. And if you've been following game development or C++, you might have seen people talk about how some of the customs we have for writing code affects performance. Over the years, we've come up with certain practices for writing code, such as solid and clean code. I think there are many good ideas in those practices, but like any other abstraction, they come with a price tag, and we should be aware of what that price tag says. Our customers don't care if the code is clean. They don't care if you follow solid. They don't care if you use Scrum or Kanban or something else. They don't care if you work from the office or from home. None of this matters to them. They care about the software that you write, and they care that it works, and they care that it has acceptable performance. So recently, Casey Moritori of Computer Enhance and Handmade Hero and other cool projects did an online lecture on how clean code affects performance of code. He took one of the examples from the clean code book and compared the performance of that code with the performance of the code he would write to solve the same problem. If you haven't seen this, I highly recommend it. Moritori is a great source of information if you're interested in performance. I think it's fair to say that this blew up on the internet. A lot of people commented on it. There are videos about the video. People are writing blog posts about the debate. And Robert C. Martin and Casey Moritori had a long discussion that you can find in a repository somewhere. I don't think the discussion is interesting to go into today, but at some point, Martin tweeted this. I've commented on this before, he says. Clean code is made for programmer performance, not algorithmic performance. If you need the latter, then write in C or assembly, or live with the high cost of development. I think there are two statements here. One is mostly a rhetoric trick. You don't have to use C or assembly to get good performance. We can write slower or faster code in any language. Sure, we might be able to get even faster code if we turn to low-level languages, but it makes no sense to say that we cannot care about performance unless we use C or assembly. I think the other statement is a lot more valid. He says, this is a trade-off. We write clean code to make us more productive. Trade-offs are like the bread and butter of performance world. Like we constantly trade one thing for another. A cache is a trade of memory for time. We do this all the time, and I think it's a completely fair thing to say. So Uncle Bob's argument here is clean code makes us more productive, perhaps at the expense of some performance loss. I think that's fair, but I think we should also be aware of the exchange rate. Exchange rate here, sorry. So let's say we can make programmers 50% more productive, and our code gets 1% slower. I think that sounds like a good deal. But what if we reverse the numbers? What if you get 1% faster at your job, but your code runs at half the speed? Your mileage may vary here, but obviously there are configurations of this that is acceptable to all of us, or some of us, and there are configurations that is completely unacceptable to some of us. Now, the interesting thing is no one has really offered any data on how much more productive we get. It's, we don't know, and it's not an easy thing to figure out. McKinsey recently did a thing and just ignore it because it wasn't helpful. Uncle Bob claims that it's obviously better, but he doesn't offer any support of that claim. He just says that it is, and that's it. Measuring performance, on the other hand, is something we can do and we know how to do. So at least, even if we don't have both sides of the equation, we can figure out if clean codes make the code faster or slower, and then we can have a discussion. Is this good enough? So The problem they're trying to solve is a very simple one. It's the one from the Clean Code book, and it's the same one that Moritori covered in his video. The original code is in Java. His implementation is in C++, and we'll do a C# implementation. And the task is simple. We want to calculate the sum of different areas for different shapes. Clean Code says that we should have a type for each shape, and we should encapsulate the knowledge of how to calculate the area for that shape within each type. If we have an abstract base class or an interface that defines an abstract property called area, we can have specialized versions of shape that each provide their own implementation. This is what a rectangle could look like. So this is how we calculate the area for a rectangle. In OO, we view the world as objects constructed from classes. So I think the model we just built feels very natural to us. And it's probably the approach most of us would take in C#. But if we take a step back and try to look at this differently, on my sort M5, I programmed in BASIC because that's what we all did back then. And we didn't have the concept of classes. But obviously, I could have written a program that calculates the sum of these areas. Maybe we don't need a class hierarchy, and maybe we don't need 5 types for this task. But now that we do, it's actually simple, right? We can easily calculate the sum of those areas. We have a collection of shapes. We run through it. We call the property, area property. We get the correct value, and we add it to the sum. It's very simple. Because area is a virtual property, we get the correct value for each shape. And the code is simple, straightforward, easy to understand. It's just a simple loop and a little bit of math. If we want to be fancy about it, we can use ling and do the whole thing with a one-liner as shown on the right. So the code is really simple, but let's take a look at what's going on. We know that we have a state machine for the enumeration, and we know that through polymorphism we get the correct area for each shape. And then there's a little bit of math to calculate the sum. It's very similar to the code, but there is additional work under the covers to handle the virtual dispatch. The ling version is a bit harder to reason about, right? We expect it to do something very similar, but just by looking at it, we cannot tell if it's doing more work. It could be. Raise your hand if you think the ling version is going to be the same speed or faster than the loop version. There's a couple of people who think ling is going to be faster. It isn't, at least not in this case. In fact, it's about 30% slower. So it must be doing more work. I don't know what additional work it does, and I don't really care here because we're trying to make things go faster, not understand why ling is slower here. But it does more work. So let's try to implement the same thing, but without using polymorphism. So instead of having multiple types, we'll just have a single struct to hold the data and an enum that tells us what kind of shape we have. We use the enum value to calculate the appropriate area for each shape. The code to sum all the areas is almost identical to what we had in the clean code version. Instead of accessing a virtual property, we're just calling a static function that gives us the correct area. Switching on an enum, of course, is considered bad practice according to clean code. But to be fair, the code is not really more complex, is it? If nothing else, it's actually a lot less code. So both projects are very small, but the clean code version is the larger of the two. Like we have multiple types and consequently multiple files. We have more than twice the lines of code. And obviously, this is a simple example. I don't think that this necessarily expands to the entire world. But I do think we all recognize a pattern here. In object-oriented code, we often end up with quite a lot of code, even for simple projects. That's not a problem in and of itself. If you're happy with this code, by all means do this. But it kind of instinctively goes against the idea of programmer productivity, doesn't it? So while productivity can be hard to measure, the performance of the code is not. So let's see if the clean code compares to the how the clean code compares to the switch-based version. So the switch-based version is about 20% faster for both smaller and larger collections. Whatever the runtime has to do to call that right version of area comes at a cost. Is 20% a lot? I don't know. I guess it depends. It's the same as cutting your work week from 5 days to 4 days. So, maybe it is worth talking about. The point is that clean code doesn't obviously make us more productive, but it does hurt the performance in this case. Just getting rid of the virtual call gave us a 20% performance improvement. But let's see if we can do even better. When we group all of the calculations in the same place, like this, we get a bit of overview of what's going on. Instead of having it in 5 different files, we have, 4 lines of code right here. Is there a pattern? Well, it looks like we're always multiplying the two properties. And then for the circle, we're also multiplying it with pi. And for the triangle, we are dividing the result by 2. And we can generalize this, right? We can do the multiplication, and then there's a multiply that we can add. Or multiply, sorry. In the case of the circle, it's pi. In the case of the triangle, it's a half. And for the two others, it's just 1. So that means that we can get rid of the switch statement. And getting rid of branching is phenomenal for performance. We can replace the switch with a simple table lookup of the different modifiers. We can arrange the modifiers in a table matching the enum for the shape. That way we can replace branching with a table lookup. We also have to make sure that both width and height are set to the right value. So for a square, we would put the same value in width and height. So when we multiply those, it's the same as multiplying width by width. The getArea function becomes even simpler, as it no longer has to switch and type. It just does a table lookup. And the summing code is virtually identical to what we had. So the question is, how is the performance? The table-driven version runs in just 15% of the time. Let's do the math on that. That's 7 times faster than the baseline, 9 times faster than Link. It's not obvious that clean code has improved our productivity, but the numbers show that our code is 7 times slower than it needs to be in this case. And keep in mind, we haven't optimized anything. We have just removed the unnecessary steps, and this code is still very, very simple. I think 7 times is a huge difference. But let's revisit Petrovsky's point. So here's a graph that shows desktop and laptop CPU performance for the last 20 years. For desktop CPUs, we peak at just shy of 24,000 whatever units these are. And we have to go back to around 2010, 2011 to get 1/7 of that. While the laptop graph is different, it actually amounts to the same thing. We still end up around the same time frame. So in both cases, we are throwing away 12 to 13 years of hardware improvement when we use clean code. What kind of productivity offsets that? So we saw massive speed up just by making the code simpler. We haven't actually optimized anything, We have just trimmed away the unnecessary parts. In other words, we removed the pessimization. What happens if we optimize the code? Optimizing the code means looking at the task at hand, looking at the data, looking at the hardware, and then measuring different ways of approaching this and seeing what we can do. What kind of performance can we get if we do that? So I went ahead and did the simplest optimization I could think of. And here are the results. The optimized version is 25 times faster in both cases compared to the clean code version. That is a massive difference. And it shows that there's a lot of room for making code runs faster. So let's recap. According to Uncle Bob, Robert C. Martin, clean code allows us to be more productive, at the expense of runtime performance. As we saw, we had to write more code, and the performance was horrible, to use the word of Casey Muratori. We also saw that using different approaches yield very different performance in C#. We don't have to turn to C or assembly to get code that is significantly faster. Whether you prefer one thing or the other is up to you, but I believe that we should all be aware of the trade-off here. We are giving up a lot of performance for claims of increased productivity. Question? No, because that's not what Robert C. Martin is doing. I took his code. I'll show you what I did, but no, I did not. I'm just showing you that we can optimize the code even further. And you know, if you're like me, you might have zoned out a little bit on that previous slide because you were thinking about what did he do to optimize the code. And as I said, I didn't do anything clever. I did the simplest thing I could think of. So what are we trying to do here? It's basically just doing a bunch of math. And CPUs are really good at doing math. And they have instructions that can do this very efficiently. So if we write the code correctly. So the most obvious way to do this is to use vectorization. Here's a layout of a recent CPU. They're getting quite complex, but we don't have to dig into the details. You need to know about two things here. You need to know about the front end and the back end. The front end is what fetches and decodes instruction from memory. So it takes a piece of memory, says, here's an instruction, what does that amount to? And then translates that into what's called a micro-op, and it sends that to the back end, and the back end will then execute that micro-op. Fetching and decoding takes time, and when we're in a high-performance scenario, it matters. So modern CPUs try to cram as much data into a single operation as possible. And that's the idea of vectorization. We try to do the same thing on multiple pieces of data. The CPU will try to do this automatically. That's why you have instruction reordering. It tries to be clever and cram as much data into the execution slots as possible, and that's what generally speeds up a lot of operations. But when we know that we are writing math code, we can do this explicitly and generate the appropriate instructions. So here's what we do in the regular approach, right? We take a height value and a width value, we multiply them, and then we take a multiplier and multiply that onto the number we just got, and that gives us a result. Then we do the whole thing again for another set of values, and so on and so forth. In the end, we'll do 2 multiplications for every set of height and width to get our result. With vectorization, we let the CPU work on multiple elements at a time. Vectorization is supported directly in .NET by the vector of T class. It takes a span, which is a way to create a lightweight slice of an array. It's essentially the C# equivalent of a pointer and a length. Through operator overloading, we can just multiply vectors and the compiler will generate the appropriate vector instructions on the CPU. In this case, we take 4 heights and 4 widths and multiply them. This gives us a new vector. Then we multiply that vector with a multiplier vector, and then we get a vector of results. Then we do the whole thing again with a new set of heights and widths and multipliers. And by using vectorizations, we're doing multiple calculations at the price of 1. And obviously, this speeds up things significantly. So let's look at what kind of code we have to write this. And this is more complex than what we had before, but it's not very hard to understand. So let's walk through it. The first thing we do is we ask vector of double for a count. What does that mean? Well, different hardware has different capabilities. So essentially, we're asking the hardware, how many of these can you do at a time? And we get that from the count property on vector. Then we loop through the different data sets in increments of that count, right? If we're handling 4 at a time, we take 4 pieces of data at a time. Then we create a vector of widths and a vector of heights. And vectors are created from spans, and spans are value types. So there are no allocations here, right? There's just take a slice into this array, take the data for this, and pass it over here. There's no allocations. It's really, really efficient. Then we multiply those two vectors and get a new vector. Then we create another vector of the multipliers, and we multiply those. And finally, we use vector.sum to say, here's a vector with some number in it. Go and add all those numbers and add that to our total sum. So, and that's how we make code 25 times faster than our baseline. But wait, we are still only using one core. As we saw in the beginning, CPUs have lots of cores these days. If we're going full steam ahead with vectorization on this machine, we're still only using 3% of the potential capacity. Now, in theory, we could make this another about 30 times faster. In reality, this is such a simple task, and there is overhead in splitting up the data, starting threads, and coordinating all of that work across different threads. So we might not be able to go completely wide on this, but we can at least figure out if we can benefit from multiple threads. We might not be able to utilize 30, but let's see how we can go here. Here's the vectorization code that we just saw, but I've set it up to run on multiple cores. The core logic is the same, but now I'm also using parallel.for to distribute the work across threads. There's a little bit of extra bookkeeping, but otherwise the code is very similar. And we can try different number of threads just to see what's the best trade-off here. The code scales well for 2 and 4 threads, but after that we see diminishing return. With 8 threads, and I haven't included the number for 8 threads, but with 8 threads, it does get faster, but not by much. So 4 threads is probably the sweet spot here. With 4 threads, we're 100 times faster than the baseline clean code implementation. And obviously, we're now using multiple threads, so it's not a fair apples-to-apples comparison. Like the clean code is only using 1 thread. It's not fair to compare them. But it does show that we have a lot of room for making code run a lot faster. So code does not have to be slow, and we don't have to turn to low-level languages to see real speed-ups. We saw that we can write code that's significantly faster than the clean code approach many of us would take. In this case, we would get substantial performance improvements without making the code more complex. Our code was simpler and 7 times faster than the clean code version. For critical tasks, we can go even further and optimize the code, and we saw that the code could get much, much faster if we needed. And I'm not here to tell you what you should do. For some cases, it doesn't matter. But if you, like I do, wonder why code is slower, we might want to challenge some of our habits and assumptions. So, takeaways. Keep your code simple. Simple code is faster and easier to work with. Be aware that it's easy to go down the rabbit hole of over-engineering, and performance suffers when we do. Focus on the necessary data for the task and get rid of everything else. If you're in doubt about performance, measure it. Don't guess about performance. Use real data, use real measurements. Customers do care about performance. In my experience, they don't care about clean code. If you're interested in this, here are a couple of resources. You should be using benchmark.net for all your measurements. If you ask me, it's a great library. Don't roll your own. I don't have many links here, but Adam Sitnik's has a super useful list of performance resources. It's really, really long. It has books and videos and seminars and whatnot. It's a very good one-stop for performance info. Obviously, anything Casey Moritori has done on performance, I mean, I'm basically ripping off his whole point here. So, go and watch the real thing. It's great. Everything he does about performance, I think it's worth looking at. If you're interested in what we do in game development for optimizing performance, take a look at Mike Acton's talk on data-driven design, which has a lot of the same thoughts that we just went through. Great talk too. And that's it. Thank Thank you. I don't know if I have time for questions. I have 3 questions or 3 minutes or 3 people or 3 of something. Any questions? Mess. Oh, you did.
In your example, you started out having a table of 4 different multipliers.
Mm-hmm.
And in the optimized one, you seem to have a vector of multipliers
Yeah.
as long as the others. So
Yeah.
there's been some trick somewhere.
Good observation. I don't know if I want to call it a trick, but a common trick in optimizing code is to recognize that arrays are really the most efficient way to keep your data. So instead of going in and out of a smaller array, I simply expand all of the different multipliers for the given types into an array of its own. So all I need to do is take the data and the multiplier, and now I have those in arrays, which is, you could say, slightly more complex, but is a very common trick for optimizing code. Good question. Anything else? I have 2 fingers left. Okay. Thank you so much.